Okay, question number 1, we have to find an equation. So we either lay down y equals mx plus c, or we lay down y equals y minus y1 equals mx minus x1. Of course, that's only if the line is not vertical. If the line's vertical, you don't use these. You just say x equals 3 or x equals negative 2 or whatever. If the line's horizontal, it's usually quicker to say just y equals something or y equals negative 1. But we've got no indication that this line is horizontal or vertical, so I'm going to use one of these. This one is great when you're told a point that it goes through, because the y-coordinate of the point that it goes through just goes there. The x-coordinate of the point that it goes through just slots into that space there. Now we need to work out m. Number of ways to work out m. There's calculus, there's all sorts of techniques, but if you're told that it's parallel or perpendicular to another line, you can steal the gradient of that line. How do I work out the gradient of that line? Just get y by itself. And then compare it to this template. You can write it in a more natural order if it helps you make the comparison. It's crystal clear to me now that m is negative 2/3, so therefore our gradient, the gradient we want, since it's perpendicular, is not negative 2/3, that would be if it was parallel. We want 3/2, because when two lines are perpendicular, then their gradients multiply to give negative 1. That means that they're negative reciprocals of each other. So that equation there is our line, and you should tidy this up and make it so there's just 3 terms. Either have x by itself, y by itself, or a 0 by itself. If I double everything, I get this. Multiply out that bracket, and so my final answer is 2y minus 3x plus 1 equals 0. That's an example of when you tidy it up by making 0 by itself rather than y by itself. Question number 2, just a straightforward trig equation in the first instance. Tan alpha equals negative 1.5. Sometimes, if that had been a negative 1, you just do that by general knowledge, like you're supposed to know that tan of 45 equals 1. But for this, you just fish it out of the calculator using the shift button. So, shift tan negative 1.5. You don't even have to type in the negative 1.5 if you don't want, because what you get now is 56.3. Notice I haven't even bothered to copy out the dash there, because it doesn't make any difference, because what you now do is tuck that 56.3 against the x-axis 4 times, producing this thing that I call the X-wing fighter. Now you cut down the 4 possible solutions to 2. Since tan is negative, we want that one, and not this and not this one. Those are rejected because that is where tan is positive, and that's where anything is positive. So we don't want them because tan is plainly negative. Now, remembering that that's 56.3, and remembering that we're only allowed to use angles between 180 and 0, we now ask, how can I get to these? Well, you can't get to that one if you're only allowed to turn 180, because remember you start there, go anti-clockwise. So that's the only one you can get to, so therefore alpha equals 56.3 to 1 decimal place. No, I don't know why I said that. I meant go 180, come back 56.3. So therefore the answer is 123.7 to 1 decimal place. So that's the answer for Roman numeral part 1. What about Roman numeral part 2? Same sort of thing. Sine beta equals 0.2. So I don't know that from general knowledge. So I just go shift sine 0.2. You get 11.5. This time you want that one and that one, since anything's positive there and sine's positive there, tan's positive there and cos is positive there. So now you think, how do you get to them? You're only allowed to use angles between 0 and 180 again. So how do you get to that? Just go up 11.5. How do you get to that? Go 180, then come back 11.5. So the two answers are 11.5 to 1 decimal place. Or alternatively 168.5 to 1 decimal place. So that's the answer to Roman numeral part 2. Question number 3, we have to find the equation of a tangent. So I'm going to use this template for the equation of a line. I want to leave that, and I want to leave that because the equation of a line is supposed to have algebra in it. But that, and that space I fill in. These are dead easy to fill in like I did for question number 1. Just take a y coordinate, put it there, take an x coordinate, put it there. As long as those two come from the same point, then it's sweet to fill in those gaps in that way. How do you work out m? In question 1 I worked it out by using a line that was perpendicular to. Here I'm going to use calculus. So here's my multiple choice box. The top is nice and tidy. So the derivative is this times this. Reduce that by 1. You should learn that that disappears, and whenever you just have a number times x, just simple x, the derivative is just that number multiplying by x. In other words, the derivative of a linear expression is just the coefficient of x. So we now substitute into this. 4 places to substitute in, that's why it's called a multiple choice box. Could substitute in there, there, or there. Do we have any basis to say what y is? Yes we do. We could say that y is 9. Do we have a basis to say what x is? We could say that x was 2. Remember how we know that the tangent is stuck onto the curve there? But which is most useful? Well, it's this row that is designed to find us a gradient, so that row is ridiculous. We're going to use that one. If x equals 2, then 3 times 4 plus, that's 15. So y equals 15 x minus 2 plus 9. Therefore y equals 15x minus 30 plus 9. So the final answer is y equals 15x minus 21. Okay, question number 4 is a definite integral. The procedure for one of these is very mechanical. You replace a single curly with these terminals on the left with a square set of square brackets, and these move from the left of the expression to the right. And in this, you don't write this algebra anymore, you write the algebra that would lead to that upon differentiation. In other words, you write the primitive of this. And for the definite integral, you don't need to write a plus c. By the way, when I call this the primitive, another name for it is just the integral of it, or the antiderivative. If you're not so good at antiderivatives, just get something ready for calculus and ask yourself what's playing the role of k, what's playing the role of n, and when you've got your story straight on that, replace the expression with this. That is this, and that is this. Okay, now what do? You place a single set of square brackets with a double set of regular brackets with a minus in between, and don't write the algebra anymore. Substitute this. And substitute this. And pump that through a calculator. And you get 25 over 3. Which is 8 1/3. Now, Roman numeral part 2 asks me to interpret that geometrically. In other words, what's that got to do with the number plane? Well, that is the area underneath the graph of that between, so that's like a bucket, and what I've just worked out is the area between area under that graph between 1 and 3. So 8 1/3 looks like it's in the ballpark for just how big that area would be. So that's question number 4. Okay, question number 5. The train accelerates from rest from a point O such that t seconds the displacement is given by this. The acceleration, so this is the topic about motion. That could be SUVAT, or it could be the 3-line multiple choice topic, where the second line is velocity and the third line is acceleration. You can only use SUVAT if the acceleration is constant. I don't yet know if the acceleration is constant. But in fact I'm being asked to show that it is. They've even told me to use calculus, which is what I would do anyway. So differentiate this, that times that is 3, reduce that by 1. The derivative of that is just 2, and that disappears. Differentiate again. The derivative of a linear expression is just the coefficient of the t or the x. So there we go, that's Roman numeral part 1. The acceleration is 3. Now what's the velocity after 5 seconds? That's the whole point of that row. It's substitute into, so I said it was 5 seconds. So therefore it's 13 meters per second. I just picked those units up from reading the general setup of the question. Question number 6. N is a positive integer, and n minus 1 and n plus 1 are 3 consecutive integers. I'm just going to get that straight in my head. So for example, if n was 12, that'll be 11 and that'll be 13. So just reading that with a 12 there and that with a 12 there. So they're certainly consecutive. All that's going on there is just getting my head around some unusual wording just by mucking around and making it concrete. Now what's my instruction? In each of the following cases form an equation in n and solve it. So this is naming, stating and equating. The 3 integers add up to 99. So there I am adding them up. That's me forming the equation. So 3n equals 99, so n equals 33. Now it doesn't ask me to say what the numbers are, but if it did, it would be 32, 33 and 34. However, it didn't ask me to do that, it just asked me to solve an equation. Now, when the product of the first integer and the third is added to 5 times the second, the result of that addition is 203. So that's same bracket twice, once with the plus, once with the minus. That leads to a difference of 2 squares. That's a quadratic. N squared plus 5n minus 204 equals 0. Is it worth trying to factorize that? Because factorizing is certainly one way you can solve a quadratic. I'm just going to prime factorize this. That's 4 times 51, which is 4 times 3 times 17. Oh yeah, that's going to work. Because what I've just discovered is that 204 is 12 times 17. That's classic use of the prime factorization strategy to handle big numbers. So, in the classic way, I wonder how would I get n squared from a bracket expansion? N times n will certainly do the job. How would I get 204 from a bracket expansion? I've just discovered that 17 times negative 12 does the job for that. The nose would be 17n, the mouth would be negative 12n. That certainly leads to 5n, so these brackets are good to go. So therefore n equals negative 17 or n equals 12. We're told that n is a positive integer. This is just me checking back to make sure I've answered the question. So therefore I have to exclude that answer. Question number 7. Solve algebraically the simultaneous equations. Now for this I'm going to use the principle that two different ways to work out the same thing have to give the same answer. I've been given two different ways to work out y. So therefore those two ways have to be the same. So that's quadratic. Two of the three ways to solve a quadratic require there to be a 0 there, so I'm going to make a 0. Going to take away x from both sides. Take away 7 from both sides. Oh wait on, that should be a 4. That's chocker with negatives, so I'm going to times everything by -1. So x equals 2, and therefore y equals, could use that, this one's simpler, y equals 9. So just checking what I was asked to do. Was I asked to provide a point of intersection? No, I wasn't in part 1, but I'm in part 2. What I've just discovered is that the graph of that and the graph of that meet at 2, 9. Question number 8. Given this polynomial x cubed plus ax plus 6, a is a constant, doesn't depend on x, so it could be 5, could be -7, could be 10, something like that. It has a factor of x plus 3. So if we factorise that, it would be x plus 3 times some other bracketed expression. It's not always another bracketed expression, but it probably would be to get something as complicated as that upon expansion. All I'm doing there is explaining what it means to say that that is a factor of that. It just means that you could factorise this by writing this next to something else as a product. Now, find the value of a. Well, there's a shortcut for determining that something is a factor, and that, like if you want to know if that is a factor of this, you just ask when that's 0 and then substitute it in, hoping that you'll get 0. We've been told that this is a factor, so therefore, if I ask when this is 0, in other words -3, then I know in advance that if I write -3 where x is, as I'm doing now, you will get 0, otherwise that wouldn't have been a factor. So I'm just going to simplify this. So a equals -6. Just taking Miss Fell's solutions. She's got... Oh yeah, sorry, that's 21. So that's 21, so that's -7. Okay, so that's Roman numeral part 1. Hence or otherwise, solve the equation such and such. Well, equations that give 0 are super sweet to have a product on the other side, because the only way to get a 0 out of a product is if one of the ingredients of the product is 0. So it'll be super sweet if I fully factorise this. So I know it's x plus 3, so what could it be multiplying by? Well, I'm just going to do a division. So my favourite example, if you want to factorise 1001 and you know that dividing by 13 would produce something, well, do the division. When you get that number at the top, it tells you that 1001 equals 13 times 77. Simpler example, when you successfully divide 8 by 2 and get 4, it tells you that 8 equals 2 times 4. So here I'm doing the algebra version of a division. I now know that a is -7. I've left a space there because the method I'm about to use crucially requires everything to be nicely lined up. That divided by that, x squared. That times that, x cubed. Now do that times that, 3x squared. That minus that, blank. That minus that, -3x squared. Got to be super careful with the negatives here. Bring this fella down. Now do that divided by that. That divided by that is -3x. And in fact, I can stop now, because I know that it's going to be x squared minus 3x and if it was a positive 6 on the end, then that just simply has to be a 2. How else could you get a 6 when you expand it? Now, I'm going to factorise that some more. So therefore x equals 1, or x equals 2, or x equals -3, and that's the answer to 8, Roman numeral part 2. Question number 9, we're told that this is the equation of a circle. We don't have to detect that for ourselves. The equation of a circle normally looks like this. In fact, they've actually told you this for free in part A. So that's the template for the equation of a circle, in the same way that y equals mx plus c is the template for the equation of a straight line when you're in year 8. And when it's in this, just like you can tell from y equals mx plus c, various things like that, that's the y-intercept, you can tell stuff from this. You can say that the radius of the circle is r, you can say that the centre of the circle is a comma b. So anyway, it's no surprise that in Roman numeral part 1 they want us to make this look like this. Well, the method that turns this into this is completing the square. Completing the square is basically a technique for reducing the number of appearances of x. See how this has physically got 2 x's on the page, this has only got 1? Well, that's what completing the square is for. I'm going to do it twice, because not only have I got multiple instances of x, I've also got multiple instances of y. So I'm just going to make a bit of an x question over here, a y question over here, and I'm going to bust that 19 over to the side. I think of completing the square as about hating what's in third position. This has got nothing in third position, and I hate that. So I create a space and get ready to fill it. What do I wish was in third position? You halve this and then square it. That's what you wish was in third position. Halve this and then square it. That's what I wish was in third position. You can't just randomly add 16 and 1 to both sides. That'll be changing the question, but you can if you're willing to compensate by adding those on the other side as well. It's not the only way of compensating for the insertion of this preferred third term, but it's certainly a great way when you have an equation and you can do red dudes. Now you factorise it. Don't bust your gut trying to factorise this the slow way. Just remember what you had at the halving stage when you were forming this 16. Whatever you had at the halving stage, that got what goes in a squared bracket. 19 plus 16 is, I think, 36. I think. Just check Miss Fell's solutions. There we go. So that's Roman numeral part 1 and Roman numeral part 2. Hence or otherwise use an algebraic method to decide whether the point 8, 3 lies inside, outside, or on the circumference of the circle. Okay. Well, just because I'm using algebra doesn't mean I can't get my head straight with a diagram. Circles are very easy to graph. Oops, don't know why I did that. So the centre is 4, -1, and the radius is 6. So if I went to the left, that would take me over to -2, -1. If I went up, it would take me to 4, 5. So that's the circle there. 8, 3. That's out here, and it's quite high. So is it inside, is it outside, is it on the line? Okay, well the radius of this is 6. So if I use the distance formula to find out the distance from the centre to 8, 3, if it's equal to 6, it's on the circumference. If it's less than 6, it's inside. If it's greater than 6, it's outside. See ya? Okay, so my strategy is to work out the distance between 8, 3 and 4, -1. Distance formula is subtract the x's. Square it. Subtract the y's. Square it. Add those two results together. So that's the square root of 4 plus the square root 4 squared plus the square root of 4 squared. So that's the square root of 32. I can tell that's less than 6 because square rooting 32 will obviously give less than giving square rooting 36. Square rooting 36 gives 6, then square rooting 32 will give less than 6. So therefore it is inside. Question number 10. So this is viewed from above. We've got a window OA, hinged there. If it's closed, it stretches to B, so obviously that's the same as that because that's the length of the window. So if it's closed, it's there. If it's open, it's there. So that'll be like a sector there. Now I know how long the window is. It's got to be 20 because I'm given that there's 8 centimeters out to this prop point and then another 12 centimeters to the end of the material. And apparently they keep the window open using this rod, which is 7 centimeters long. And apparently there's this little space. Yeah, this happens in Windows. There's this little thing that contains a little mechanism that connects this to this. If the window is the most open, I think that then slides down to there. If it's less open, that ball slides over to there. And apparently there's 5 centimeters to play with in terms of how long that is. Yeah, as it says, if it's closed, it's it. Oh, apparently if D goes all the way to the F, that actually closes the window completely. So A would then be down at B. So I'm going to draw it when it's closed. So A and B would then be together. Still obviously be 12. C would still be there. That 7 would be completely against this. So that would be a 5 over there to make up that 12. All that's going on here, by the way, is I'm just trying to understand what this setup is. And we're told, that's D by the way, that if it's closed that's actually at F, and F is the right extremity of this little bar, they call it. So that would be E, and that would be, that 7 would be made up of 2 and 5. Okay. Anyway, that's by the by, that's just me trying to understand the mechanism. Okay, so all we have to do is find the angle EOC when the window is fully open. If the window is fully open, then that 7 is actually there, I said. And that 5 is entirely to the right of that contact point. Oh, and I forgot to say that it's 10 centimeters from O to the start of this bar. So what I've drawn now is the diagram for it being fully open. So what's the angle EOC? Okay, well this is just the cosine rule now. Sorry it took me so long to get my head around this. We want this angle here, so label this up, capital A, little a. capital B, little b, capital C, little c. Three sides are engaged, so we're going to use the cosine rule. Here's the angle version of it. Got to learn that off by heart. It's not in the formula page, I don't think. Substitute what each thing is equal to. 10 squared plus 8 squared minus 7 squared all over 2 times 10 times 8. Nice big calculator with a big screen. Type that in as it actually appears. Go shift cos on all of that and you'll get 44.0 degrees to 1 decimal place. Now in part B, I want to know, oh damn, I just rubbed out my diagram. Okay, just put this in. Angle, distance OD, when the angle is 30. So that's 30, that's definitely 10 to the start of the bar, then the bar takes 5, that's still 8 and 12, they're fixed. But 30 degrees is nothing special, it's neither fully open nor fully closed. So that section there could be anywhere along this bar. And by the way, if that's 10, that's 5. That's got to be 5 as well. So OD. So I don't know where along there that rests, but I do know that it's a length of 7, that's fixed. So, just copying this out, we've got 7 there, we've got 30 there, we've got 8 there. We want the distance from O to D. Okay, so this is sine rule, I think, but I'm not sure. Not sure how I'm going to work out OD when I don't have this. So why don't I work out this first? Okay, so sine y over 8 equals sine 30 over 7. So sine y, so that's the sine rule I've used there, sine A over A equals sine B over B. So sine y equals 8 times sine 30 over 7. So I'm going to do this and then go on the calculator. I go shift, sine, open bracket so I can catch all of this, 8, let's open up a bracket there, so I'm just going to immediately close it, times sine 30, again it's open up a bracket without me asking me to, so I'll close that down, divided by 7, and the bracket equals, so y equals 34.84. 4, 9, etc. So therefore, let's call this W. So W is, draw the triangle out again, that's 30. That's 180 minus answer minus 30. So that's 115.15, etc. And we want to know this distance here. We're told that that's 7 and that's 8. So I'm going to use the cosine rule here, call that capital A, capital B, little c, capital C. So x squared equals, I'm writing out a squared equals b squared plus c squared, oh sorry, that's 7 plus c squared minus 2 times b times c cos of a so square root of, I'm just getting ready to write the x here, 7 squared plus 8 squared minus 2 times 7 times 8 cos answer. I'm not sure whether that'll let me, maybe need to put a multiplication in there. So therefore x equals 12.67 to 2 decimal places. Let's hope and pray that's what Miss Bell got. Yes it is, thank goodness.